Hello guys and welcome to today's challenge. Let's begin our question. Alright, question 129. Sum root to leaf numbers. You're given a root of a binary tree containing digits from 0 to 9 only. Each root to leaf path in the tree represents the number. For example, the root to leaf path 1, 2, 3 represents the number 1, 2, 3. Okay, return the total sum of all root to leaf numbers. Test cases are generated so that it will fit in the 32-bit integer. Okay, so there's a couple of giveaways here. First of all, that this number that is going to be from the root to leaf node fits into the 32-bit integer, so we don't have to do any complex math. We just have to turn a sequence of random digits into, well, not random, parent to child digits into a number. And then sum it all up. Let's see. Example here is 1, 2, 3. Output 25 because 1, 2 is a number 12 and 1, 3 is number 13. So 12 plus 13 equals 25. And let's see here. 495, 491, 495, 491, and 40, which equals to 1026. Okay. So the values between 0 and 9 inclusive. Depth of the tree will not exceed 10. Okay, so this is definitely probably is going to be called solved recursively. Let's see. Since we have we can have a global variable called sum, denoted as s, and then a DFS search. Let's define a DFS search. What does the DFS function take as parameters? Well, one, it needs the node that we're currently observing, as well as the number. The number is, in this case, just going to be a string because we are creating a number from we're concatenating strings and then essentially creating a number. This could probably be done in other languages, maybe like Java or I don't know, Rust, in a more integer way where the number that you pass is just the number times 10, so that you're essentially moving up. Well, actually, let's just see why are we talking without, if not node. So if I'm hitting a leaf node, then I would say non-local s, bringing s into the scope of this DFS function, and saying s plus equals int of number. So if I'm a child node, if I'm a node that does not exist, a node of this child, then essentially add number to s and return. Else, I'm going to call DFS on node left number. Let's see, this is a string, right? So it's going to be number plus str of node val. And the same thing here with the right node val. I'm then going to call DFS with root as the node and an empty string and return s. And right away we get the wrong number. We get the wrong number. Why? It seems like we are returning twice as much as this. Wait, what? For this is 50 and this is double. is it double because I'm appending 12 twice and then 13 twice? So, oh, I see. So what's happening here is that, okay, well, how about this? How about I catch the scenario of, how about I catch this, basically do this logic, not at the node that doesn't exist, but in the node that does not have any children. So how about I say if, let's see, if not node left and not node right, then I'm going to plus str node val. So I'm doing this logic, but I'm doing it here. And then would I just be actually temp? Let's say the temp is equal to number plus str node val, and if not, sorry, no, this is just trying to reduce the number of trying to reduce the number of string calls, the string concatenations. Let's see, how about this? No. If not node left and not node right, node may be already a none type, so if not node, return. No, not good at all. Let's see. How can we increase the speed of this? Well, how about instead of using string concatenations, how about I say that the temp is going to be number times 10 plus node val, right? Then I'm going to treat this as the temp, and here I'm just going to pass a 0. Better, 55. So string concatenations are very expensive, so what is another way that I could decrease this? Well, I could remove the need to execute this. Basically, I could prevent this from ever having to be executed by catching the condition here, basically by saying that if node left, do this, if node right, do this, and then removing this guy. Let's see, how does that look? Already better. Interesting. What is a better solution to this? I really don't know. Let's kind of just check quickly. Seems like so here's another approach. They don't have a global at all. They don't have a global thing to keep track of the number. That might be that might be reducing the speed a little bit. What they are doing though is they're returning they're propagating the number all the way back to the top, basically saying something like this. Saying that the return value is actually going to be DFS left plus DFS right. So I'm going to be returning this plus this, and I'm going to be returning DFS with a root, and here, how would I start adding it, right? I would start. Wait, the number of this, what would this number be? This number would be the left plus the right. And what would this be? Just the left plus the right plus me. Sorry, not there. How did they go? How did they treat the? So if not node, if I've reached the end and not a non-existing node, then return 0. Else current is equal to the current plus 10 plus node val. And if not node left and not node right, return cur. So why does that work though? If not node, return 0. Then I have the temp. And here I say if not this, then return temp. Why is this so much faster? It's not faster. Yeah, so they're suggesting basically another approach that let's see. They're building up the sum just by returning from the bottommost. So as soon as you hit the end, you start returning the sum of everything that's been built up to that point. Yeah, I guess this also works. I just don't understand why it's not as fast. 88. Ah, sweet. Okay. Well, there you go. Feel free to use. Thank you for watching. Bye.